Alright, the second example we're going to look at is simply being able to read a characteristic equation of our displacement from equilibrium provided to you here on the left, and to use what we know about the relationships between the displacement from equilibrium, the velocity, and the acceleration of this motion to find a bunch of different quantities. Alright, so typically speaking, this is actually not going to involve a terrible loud amount of problem solving, but we're going to go through them one at a time. The very first thing you've been asked to find is the maximum amplitude of this motion. In other words, what is the maximum displacement from equilibrium? It's this d equilibrium max that you have here. Now, how you would do this is simply compare the two equations. If you compare them, you'll notice that the maximum amplitude of the motion that we need is simply whatever number is outside the trigonometric function, and that's it. So if your goal is to find the maximum amplitude of the motion, you can measure it from a graph or something like that, but if somebody provides you with a characteristic equation, it is rather easy to find this. It's simply going to be the number outside of the trigonometric function. So here, it's literally just 10 centimeters, and that's honestly all that you have to do. Now, for the second part here, you're asked to find the maximum speed of the motion. Maximum speed. Now, if you take a look at this characteristic velocity equation here, I don't know how much you guys know about trigonometric functions, but trigonometric functions cannot have a magnitude that's larger than 1. In other words, the biggest that cosine can be here is simply the number 1. Therefore, what's actually going to define our maximum speed is, again, these things that are outside. Now, because we're looking for a maximum speed, we actually don't need this to be in vector form, so we can ignore all signs. But basically, this maximum speed, all we're going to need to do is take omega, the angular frequency, and multiply it by the amplitude, or the maximum displacement from equilibrium. So again, you can do this pretty quickly. At the end of the day, our maximum velocity, so our v equilibrium max, is simply going to be whatever terms show outside the trigonometric function. So this is going to be omega, which I'm just going to leave as a w, times the displacement from equilibrium at its maximum. Here, if you compare what we need here, you can take a look at this function up at the top. Omega we're actually provided with. Inside the sine function, omega is whatever thing is next to the time. So here, omega is literally 2 hertz, or 2 seconds to the negative 1, and our maximum displacement from equilibrium is simply 10 centimeters. If you multiply these two things together, you will get 20 centimeters per second. And you're finished. What you'll notice is if you compare this to example 1, this is much faster. It's why sometimes having characteristic equations can make your life significantly easier. Now, for the last one here, we're asked to find the maximum acceleration. Similarly to the previous one, sine functions are limited to be between 1 and negative 1. So to find the maximum acceleration, we want whatever's out here at the front. Now, it's important to note here that because sine can go between plus 1 and negative 1, so it can go between 1 and negative 1, our maximum speed is just going to be whatever the, or our maximum acceleration is just going to be whatever the positive quantity is here. So if you want to find your maximum acceleration, one second while I type, all you need to do is take the quantities that are out front and multiply them together. Right. So the difference here is you'll have an omega squared as opposed to the other one. Again, we can drop the minus sign here because sine will oscillate between plus 1 and minus 1. Right? So at the end of the day, we're always going to have a maximum that is indeed positive. Now, with this being said, I know that omega here is 2 hertz. So we're going to square that, and we're going to multiply it by the maximum displacement from equilibrium, which I know to be 10 centimeters. Putting this all together, you will get 40 centimeters per second squared. Again, the reason why you get centimeters is because we have centimeters here, and the reason why we get 1 over second squared, or divided by second squared down here, is because hertz is literally seconds to the negative 1. Or alternatively, if you like fractions, 1 divided by seconds, like so. Right? And that's all you need to do here. So if you have the characteristic equation, finding these key properties of oscillatory motion are as simple as simply comparing what you got to the actual numbers that you've been provided with.